Okay, here we are for our first lecture for set theory and logic. Now, before I begin covering any material, let me just try to impress upon you how important this class is if you are a math major and how seriously you need to take it, okay? This isn't the hardest class that you'll take, but it is the most important. In this class, you are going to learn how to think mathematically and logically. And I'm not talking about computation, because there will actually be relatively little computation involved here. This class is going to teach you how to think logically and how to prove and disprove statements. Okay? At the university where I was an undergrad, this class was called Introduction to Advanced Mathematics, because practically every class you take after this is going to depend upon this class. Okay? I cannot impress enough the importance not just of passing this class, but of understanding. Okay? I taught many students who passed this class, but not really well, but they still passed. And then in their senior level math classes, I just simply can't find a word for how much they struggled. Okay? This will derail you if you don't learn this stuff. So I'm not trying to scare you, but then again, maybe I am a little bit. I'm just trying to impress upon you the importance of this material. So don't just, blow this off and do just enough to pass. If you're a math major, you need to know this stuff, because almost all the classes you have left after this are going to be proof-based. Okay? And the professors are going to assume, rightfully so, that you know how to read and construct proofs. Okay? And they're not going to be able to teach you this material again in the middle of those classes, because there's other material that need to be covered in those classes. So please put in the effort this semester. You will be very, very glad that you did. Okay? And it's not going to start off really hard, so don't take this first few lectures and say, oh, he was just trying to set us up to, take it seriously. But it actually seems pretty straightforward, because the thing is, it's not going to start off hard, but it gets deeper as we go along. Okay? So don't let up on the amount of attention that you're giving to this class. Okay? All right, so we're going to start out at the beginning. How about that? That's a good place to start, right? And so I'm going to write down a couple words here, which are set and element. You probably already have used these in the past, but that's okay if you haven't. Okay, a set is a collection of things. Okay? Or if you don't like the word things, if that sounds too juvenile, we could say it's a collection of items if you would rather have that. Okay, and the next important word is the items in the set are called elements of the set. So that's the basis. Those two words are the basis of set theory. There's two parts to this class. Not a part one and a part two, really, but just two things that are melded together all the way through. We're going to do set theory, and we're also going to do logic. Okay? And these two words are the basis of set theory, is the word set and the word element. Okay? All right, now, so a set is a collection of items. Most of the time in math, those items will be numbers, but they don't have to be. Okay? Now, when we do a set, we use these curly brackets or braces or whatever you want to call them. That denotes a set. Okay? And we write the elements inside there. Usually, I'm going to show you other ways to do it as well, but for right now, I'm just going to write the set of the first 5 integers. If you don't know that word integer, I'll define that in a minute, but I'm just going to write the numbers 1, 2, 3, 4, 5 in this set. We separate them with commas. So, you know, this is kind of trivial, but it's very important, okay? Number 1, sets need to have curly brackets around them if you're going to write the set out. And number 2, the elements in the set need to be separated by commas. You don't have to write the whole set out. You can just give it a name instead. Okay, like, you know, the number pi, we can't write the whole number out, right? So what do? We give it a name. We call it pi. This is not a rule, but it is a custom that if you're going to give a set a name, most people use capital letters for the names of sets. And that's so that you don't get it confused with a variable. Usually we use lowercase letters for variables, uppercase letters for sets. Okay, so there I have a set that I've named A. And it has how many elements? 5 of them. Now, this is super important. The order that you write the elements does not matter. Okay, I can do this. I can say that A also equals this. That's the same set. Okay? I like to think of it like this. A set is a cardboard box. And the things that you see when you peer into the box are the elements. Okay? Now, if I had a cardboard box, and let's just pretend that there was 4 wooden blocks in there, and one block had a 1 on it, and another one had a 2, and a 3, and a 4, and a 5. Oh, I said 4 blocks, I meant 5 blocks. Okay? If I took that box and then shook it up, and then peered inside it again, I would probably see those 5 wooden blocks, you know, in a different order, wouldn't I? But it's still the same box with the same things in it, correct? So that's why when you rearrange the order of the elements in a set, it does not actually change the set. Okay? Easy way to remember that is people say, order doesn't matter when you're writing out a set. Okay? All right, now, when you have a set that only has finitely many elements, then it's very easy to just write them out. Well, I shouldn't say very easy. What if there's 1,000,000 elements? Then it would not be easy to write it out. But in theory, you could, right? And you would call that a finite set if there's finitely many elements. Okay? Let me introduce a word for you here. Definition. The cardinality of a set is a measure of how many elements are in the set. Okay? Look at how I wrote that. I didn't just say the cardinality of a set is how many elements are in the set. I said it is a measure of how many elements. And that's because if there's finitely many elements, then it's really easy. You just count them and see how many there are, and that's the cardinality of the set. Okay? But if there's infinitely many elements, then it gets quite tricky, and we'll deal with that later on. Okay? So, here's what we're going to use for cardinality is vertical bars. So I'm going to write this here. Vertical bars with the A in there. That looks like absolute value of A, right? But here's how I know it's not absolute value. Because A is not a number. Absolute value is something that you put around a number. Okay? Since A is not a number, then that must not mean absolute value. What is A? It's a set. So I know that those bars mean cardinality. Okay? And in this case here, the cardinality of A is 5 because there's 5 elements in A. Okay? You can certainly have a set with nothing in it. Let's do this definition. I mean, why not? Why does a set have to have something in it? Can't I have a cardboard box with nothing in it? And if a set is just like a cardboard box with, you see what's in there to see the elements. If I look in the box and it's empty, then I have an empty box, right? There's nothing wrong with that. So it's the same way with sets. A set, well, actually, I should say the set with no elements is called, well, let me ask you, what would you call a box with nothing in it? You would call it empty, wouldn't you? An empty box. So the set with no elements is called the empty set. Okay, here's what it looks like. That's what it looks like. That's the empty set. It's a set. You see the curly brackets. That means it's a set. What's in the curly brackets? Nothing. They're empty. So it is an empty set. Okay? Now there's a symbol for empty set, just like there's a symbol for pi. That is a circle with a line through it. Or, I mean, I'm not going to object if you draw a 0 with a line through it. That's also considered a correct symbol for the empty set. I just don't like it as much. I like the circle with the line through it. We don't need to get into why that is, okay? It's just personal preference. All right, let's see here. What else? I'm going to shrink this down so we can see everything at once here. Okay, so we have set and element. Notice I didn't write definition on that first sentence. That's because those are usually considered undefined terms. Kind of like in geometry, the words point and line are considered undefined terms, right? So in set theory, the words set and element are considered undefined. They're just common notions that we agree upon the meaning, but we don't actually say definition, okay? All right, and then we defined cardinality, we defined empty set. Okay, let's define some of the major sets that you've seen before in your mathematical journey. Okay, so we have, let's label this some important sets. Okay, so you have the natural numbers. And the natural numbers are whole numbers starting with 1. I'll just put an ellipsis there at the end. Okay, so that's the natural numbers. Then you have the integers, which is the natural numbers along with 0, along with the opposites of all the natural numbers. So that would look like this. I'll write in order here, even though I told you order doesn't matter, but it's still nice. So I'll write it like this. The opposite of 5, the opposite of 4, the opposite of 3, the opposite of 2, the opposite of 1, 0, 1, 2, 3, 4, 5, and so on. Those are called the integers. Okay? And it's common to use what's called blackboard bold letters for these sets. The natural numbers is usually written with a capital N like this, is how most people write it. In books, I don't really know exactly why this is, but in books, the double stroke is usually on the diagonal line. So in books, it's always typed like that here. But when people write it by hand, they almost always write it that way. Okay, so that's natural numbers. The integers is called with a capital Z, and that's just because the German word for integers starts with a Z. So that's how you write integers. Okay, so these are natural numbers, and these are integers. And I'll just point out for you that the set of natural numbers is also the set of positive integers. Notice that? Okay, now those sets are infinite, right? There's infinitely many elements. So number one, if I asked you for the cardinality of that, well, again, we would have to talk about that in more detail, and we'll get to that later. So let's not worry about it right now. Okay? Now, even though there's infinitely many of those, it's still easy for me to indicate the sets, right? By just using the ellipsis. You know what that is, ellipsis? It's those 3 dots. Even though I'm not writing out every number, and in fact I couldn't write them all out. It would take me longer than my lifetime. But it's still easy for me to indicate what the sets look like. Okay, now let's go a little bit further. What about rational numbers? Okay, well, let me go ahead and first tell you the letter for that. The letter's a Q. Again, we can thank the Germans for that. And people usually write their blackboard Qs, blackboard bold Q like that. Okay, this is the rational numbers. I'm sure you know what rational numbers are. They're fractions, right? Or more specifically, we say they are numbers that can be written as a ratio of integers. So, how many are there? There's infinitely many, correct? But I would have a hard time indicating all of them, right? Like if I wanted to do this with an ellipsis, like I did with the natural numbers and the integers, how would I do that? I mean, I suppose I could say a half, a third, a fourth, and so on, right? Whoops, what happened there? But that's not going to be good enough, is it? Because even I do that, I still have not even scraped to the top of the iceberg, right? There's so many more rational numbers than there are integers. Or are there? Well, I don't know. We're going to have to discuss that later in the semester. But I can definitely tell you that I'm having a hard time figuring out a way to write down all of the rational numbers in there, or to write down, something that would indicate all of them. So I'm going to show you a new trick. When there's just too many things to write down in a set, we use what's called set builder notation. Okay, and I think the best way to do this is for me to just write it and then point out the different parts for you. Okay, so here's what I would write. There's a couple of ways of writing it. Okay, I'm going to write it my way, and then I'll also write it the way that it is in the book. So here's what I would write for rational numbers. What do they all look like? They all look like integer over integer, right? Except the bottom integer can't be 0. So I can write this, m over n. Okay? And then I'm going to put a colon here. Nice big colon. Okay? And then I'm going to say m comma n, this fancy little symbol that looks kind of like an E, integers. Oh, and also that n can't be 0, right? Okay, let's look at that. What do you think this thing means? It looks like an E, doesn't it? Have we defined any words so far that start with an E? Oh, there's one right there, elements. Well, guess what? That symbol is the symbol for is, or in this case are, since it's plural, there's 2 numbers there, are elements of. Okay? I should go up, I'm going to scroll up there, and we're going to write that down next to the definition of element. Okay, I'm going to write X, and then this thing. It also looks kind of like an epsilon, doesn't it? But it's technically not an epsilon. Okay, so that means X is an element of the set A. Okay, so let's go back down to where I wrote this and let's dissect what I wrote. So let me read this for you. I'm going to highlight as I go from left to right, and I'll say the words that go along with the symbols. Okay, so it says Q equals the set of m over n such that, that's what that colon stands for, such that m and n are elements of the integers, and then the rest is easy, and n does not equal 0. Okay, so I'm going to say it again all at once now. Q equals the set of m over n such that m and n are elements of the integers and n is not 0. Okay? Now, that colon, that means such that. I find a lot of students, oh, I accidentally erased our Q. I find a lot of students don't like that colon and prefer instead a vertical bar. You can do either one right here. Either a colon or a vertical bar, but either way it stands for the phrase such that. Only in this is called, I should write this down. When you do this kind of notation here, this is called set builder notation. And when you're doing set builder notation, that vertical bar or colon, whichever you prefer, stands for the phrase such that. But it's the only time that a vertical bar or a colon means such that. Outside of set builder notation, you do not use a vertical bar or a colon for the phrase such that. Okay? Now in the book it's written slightly differently. I personally think it is a bit overkill, but this is how it is in the book. I'll just show you. It says, the set of all x such that x equals m over n, where m and n are integers and n is not 0. So look at what I wrote in gray and what I had previously wrote in black. I hope you can agree that that says the same thing. I think the way it's written in black is more efficient and more concise. Okay, but if you like the way it is in gray better, that's fine. Okay, I'm going to erase it for now. So you see, let's summarize. An empty set is called the empty set, and that's how you write it, either the circle with the line through it there, or literally a set with nothing in it. Okay, a finite set is easy to write because you can just list the elements out and put the brackets around them. Okay, or you can give it a name. Infinite sets tend to be harder to write because there's infinitely many things, but if it's not too complicated, you can use an ellipsis, or in the case of the integers, I needed 2 ellipses, or ellipsi, I don't know. Okay, and then if it gets more complicated than that, then you can try set builder notation. Okay, now here's another one. What about the set of real numbers? So that one we call with a blackboard bold R. And I'm not even going to bother trying to write that in set builder notation. Okay, it's just, I mean, what would I write? The only thing I could think of would be to write, it's the set of all x such that x is a real number. But clearly that's not going to suffice, because then I'm just using, it's circular, right? I'm just using the real numbers to define the real numbers. So real numbers is really, it's really almost like an undefined term itself, just like the word set. Okay, it's just a common notion that we kind of have to agree on. You can define the real numbers and give it an actual definition. And if you take real analysis, you'll probably do that. But for right now, we're just going to take it as an understood concept. Okay. All right. There's also complex numbers, by the way, and we're not going to worry about that right now, but here's the symbol for complex numbers. But I'm going to erase that. I don't want to leave that on the screen. Okay. Let me think of where we are and what we still need to cover. Well, what about intervals? We should talk about intervals. You've used those a lot in previous classes. So let's scroll up here, okay. And let's write intervals. Okay. So, what kinds of intervals have you seen in previous math classes? You've seen ones like this. That's what we call a closed interval, right? And you've seen ones like this, which is called open. And you've seen intervals that look like this, and ones that look like this. Those are all finite intervals, okay? a closed interval, an open interval, and then two that are neither. Okay, but they're all four finite. And then what about infinite intervals? You can have something like this and something like this. You can have something like this or this, right? And I can think of one more, and this one's not listed in the book. It's kind of surprising because it's very simple, and that's this interval. Okay, so let's write down all of those in set builder notation in order to give them an actual definition. Okay, so the first one, what we call the closed interval from A to B. What is that? If I asked you what is that, you would probably say all the numbers between A and B, including A and B, right? But how about, let's write that using mathematical language and symbols. Okay, so here's how I would write that first one. I would write that thing equals the set of all x's in the real numbers such that x is equal to or greater than A and less than or equal to B. See, I'm using set builder notation to give an actual definition for the closed interval from A to B. Okay? And then for the open interval, it would look the same, except without the equals. So I would say the set of all x in the real numbers such that x is greater than A and less than B. Okay? The next one would be the set of all x in the real numbers such that x is equal to or greater than A and less than B. So go ahead and think about how you would write the remaining, well, let's leave the last one by itself for now. Let's just say the next five. How would you write those? Oh, and I see I accidentally repeated myself down there where I meant to put a parenthesis. Okay, so take a minute and write, or at least just imagine in your head, how would you write the next five intervals with set builder notation? I'm going to pause for a second and then I'm going to just write them all out. And then you can think about what you wrote or what you pictured in your head. See if you agree with the way I'm writing it. Okay. All right, now what about the last one? Well, the last one's very, very different, isn't it? The last one is actually the set of all real numbers. Okay, so now you have actual definition for these intervals. All right. We're just about done. Let's see where we are on time. It's been 35 minutes. I think we're going to stop here, okay? Some of the lectures will be longer. Many of them will be longer, let me say. But this is just the first lecture, and I just want you to get comfortable with the symbols and the words involved in writing sets and elements, and especially set builder notation, okay? And we will continue from here in the next lecture.